Okay, so in this session, I'll be talking about electrodynamics and optics. So specifically, I'll be looking at radiation and scattering. So first of all, we start with saying that we have some source terms. So for our Maxwell equations, our source terms are the current density and the charge density. So let's say our charge density uh, and current density is rho and j respectively. So our scalar potential phi is going to look like something like this. Space. Now this this is a retarded time because what happens is if you change your source term at some distance away from the source, it takes time for the change to propagate. So it propagates at the speed of light. So you have to evaluate the source at some previous time. And we have a similar expression for the vector potential. J r prime p minus r minus r prime over c. Yeah, so what we're saying is we evaluate each contribution of the source terms and we take into account the sort of phase change they would have because of their retarded time. Now, if we have something like a constant velocity, like if we have a charge moving at constant velocity, then in the rest frame of the charge, you can't have radiation. So if you can't have radiation in the rest frame of charge, then you can't have radiation. So when we talk about radiation, we're only interested in accelerating charges. There's some slight subtleties there, but for now that's sufficient. Constant velocity, now there's Cherenkov radiation, but that will not be covered today. So now let's look at an electric dipole. So here I've got a diagram of my electric dipole in this green arrow. So say it's free space, and this dipole is something like P at the origin O. So what happens to the E field at X, at some point X? So initially the field is going to look like this, the arrows point this way. If we imagine we suddenly flip our dipole, then the arrows are going, like the fields are going to point the other way, but at some point away, like the signal hasn't propagated there yet, so they are still in the original configuration, and this diagram is a massive simplification, like, but it's just to illustrate my point. So only after some time later, like, so after a time r over c, where r is the initial separation from the dipole of the point we're measuring it, only after this time will the signal propagate to the end and we get the new field completely. So now what happens if we keep flipping our dipole? So let's imagine that we have a dipole moment of the form p naught e to the negative I omega t. So some oscillating dipole. Then our electric field will have some dependence e to the negative I omega t minus r over c. So this has to depend on the retarded time. So if charges oscillate here to create this dipole, then we have currents because you have changing charge. And that implies you have a magnetic field at X. Now, let's look at a Hertzian dipole. So I have a diagram here. So what we have for a Hertzian dipole is each charge. So we have something that looks like that. And then this is plus Q, T, and it's equivalent to Q, e to the, say, negative I omega t, Q naught, and then this is minus Q, T, so say negative Q naught e to the negative I omega t. So our dipole moment is the separation between them multiplied by just multiplied by the charge of each, and we have a current flowing between these two because they are changing. So because their charge is changing, so there's going to be some current flowing between them. So the current is the rate of change of the charge, which is negative I omega q naught e to the negative I omega t. And this is equivalent to saying that it's negative I omega p naught over d e to the negative I omega t. Now, when I say p naught, well, what I've written here for my dipole is that I've actually missed out some vector notation, but I can write my dipole as something like this: q naught d e to the negative I omega t, and I can equivalently say that 0, 0, some dipole amplitude, and then multiplied by some sinusoidal variation. So for our what we call a dipole approximation, we're basically saying that the dimensions of the dipole is much less than the wavelength of the radiation is emitting, and it's equivalent to 2 pi c over omega. So what this is saying is that basically you are, well, not really concerned with phase variations within the dipole itself. It's more the retardation that is the factor. So I mean, what I mean by that is if I have a really long dipole, it looks like that, and say my radiation, my lambda, my wavelength is something that like that, then it depends, because like just measuring it from these 2 points will introduce some phase difference. So yeah. Now with the dipole approximation, we can say that from our previous expression for the vector potential, it's equal to mu naught over 4 pi. Now this square bracket notation denotes the retarded time. It just says that we're evaluating it according to the retarded time. And then in the next step, we impose the dipole, well, we impose the approximation, the assumption that the dipole's dimensions are much less than where we measure the distance to where we measure the field at. So it becomes something that looks like this, because we can just ignore the denominator here and say that, treat that as almost a constant. So this thing, integrating the retarded current density, simplifies down here, because we know that our current is only flowing in one direction, which is the z direction. And so this becomes I, then because we're integrating over volume, so d z hat is actually something that looks like j and then a d, where this becomes the volume term, yeah, and j is the current density, and this is equivalent to q dot t minus r over c d z hat. It's equal to p, the rate of change of the dipole moment z hat, and we just say that this is the retarded dipole moment. So our final result is that mu naught over 4 pi r p. Now this a, we know that it's only going to point in the z direction because of how the dipole moment is pointing in only the z direction, and we can work in spherical polar coordinates. So say this negative a sine theta and a phi is 0. This holds by cylindrical symmetry. And so if you look at, now we look at the scalar potential, phi, we get rid of the phi dependence by imposing cylindrical symmetry. So this is a very standard way when we deal with dipoles. We just say consider the two charges that are separated by some small distance, r minus over c. I mean, what we're basically saying is let's consider the sum of the potentials of each. Do the math, we get phi is going to go to cos theta over 4 pi epsilon naught p over r squared plus p dot over rc. Now, say we want the electric field. We know it's got the form negative del phi. Oh, actually, let me just use phi to prevent confusion. Minus a dot, and the magnetic field is the curl of the vector potential. If you do the math again, then you can get that the only non-zero components for these two fields is going to look like theta over 4 p dot over r squared plus p dot over rc e theta is sine theta 4 pi epsilon naught p r cubed plus p dot over r squared c plus p double dot over rc squared. And finally, the radial component of the electric field r cubed plus p dot over r squared c. So just pause for a moment. Let's just look at what some of these are telling us. So let's look at the e theta components first, right? So this one. So first of all, we have an r cubed term, we have an r squared c term, and we have an r term. The r cubed term looks like just, well, a static dipole, yeah? And this goes for here as well. It's basically the field we would get if we just have a dipole. So we call this the dipole term. This tends goes as something like that. Call this the dipole term. And because it's r cubed, it's going to dominate when r is small, relatively speaking. So when d is much less than r and much less than lambda, then it dominates. Now, what about the second term? So this p dot over r squared c term tends as p naught over r cubed, 2 pi r over lambda, r cubed. And this is what we call an induction term. Well, it's sandwiched between this r and this r cubed, so it's never going to dominate. And we can see that the last term, because it's only dependent on one of r, it's going to dominate when r gets large. So the last term, which is over rc squared, which goes as something like r cubed 2 pi r over lambda squared, is what we call the radiation term. Radiation because, well, p double dot seems to imply some sort of acceleration, whereas p dot implies some sort of velocity, which is why we get an induction term. But So this dominates when you have a large R, so much bigger than your wavelength and much bigger than your dipole dimensions. So in the far field, yeah, we take E theta to be sine theta, so far field, sine theta over 4 pi epsilon naught p double dot over r c squared, and the magnetic field. So the radial field drops out because it's only got dependence on p. I mean, it's same dependence on r cubed, but this is a p factor. So it's p double dot over rc. And you would sort of expect the radial term to drop off because if it's a dipole, it's quite weakly it's quite weakly dependent on the radius. Because as you go, well, you can think of it this way: as you go further out, the dipole looks more and more like a point source. So, and not just a point source; it's a point source with two opposite charges, I guess. So radial term disappears. Right. And so what we can note from these two is that it's actually related by a factor of c, as we won by EM waves. And also the E field and the B field are mutually perpendicular, which tells us that the Pointing vector is just going to be radially outwards, which is also nice. So let me just go here. So this is a typical angular dependence for the power radiated by a dipole. It's a torus, and well, we'll roughly see how we get that. So the Pointing vector is of the form this form. So what we can note in the induction fields. So just now induction fields, the induction terms we talked about were something like 1 over r squared. So now it becomes something like 1 over r to the 4. It's not net outward flux, first of all, because, well, if it's 1 over r to the 4, it's going to decay really quickly as you go out. It can't be something that radiates power outwards, you see. So it has to be something that redistributes energy close to the dipole. Energy close to the dipole. Now, in the far field region, what we can say is our Pointing vector, if you do the math, it's going to look like something like E theta B phi, which is going to be mu naught over 16 pi squared C sine squared theta P double dot squared over R squared. And this is the angular dependence of the radiated power. So it's a sine squared theta dependence, which is why we get the torus. If it will load. Yeah, which is why we get the torus. That's pretty important to know the form of the radiated field, like the power. And we can also note that this is decays as 1 over r squared. So the total, if we want to find the total radiated power, right? Well, roughly the total radiated power. Let me just rephrase that. This would be the surface integral of the Pointing vector, and we roughly know that the surface is going to scale of something like r squared. So you wouldn't see any R dependence in the total radiated power, which is what we expect by conservation of energy. And so it's going, if you do the math again, you would get something of the form P double dot squared. So for example, if I take my dipole moment to be of this form, this oscillating form, then P double dot would be negative omega squared P naught e to the negative I omega t. And this tells us that the average of this term is also the same as the average of the non-retarded term, which is this. So something that depends on the frequency as omega to the 4. And our result is that the average Poynting vector looks like P naught squared over 32 pi squared c sine squared theta over r squared. And this is an average over time, just to make that clear. And the average of the power looks like 12 pi c omega to the 4 p naught squared over 12 pi epsilon naught c cubed. Okay, so just now we were talking about the dipole, the Hertzian dipole to be precise. Now we'll look at a more general case for our source term. Is rho of r and j of rt. So we're imposing some sort of sinusoidal variation with time on these two. And what we'll get is a vector potential that is of the form mu naught over 4 pi. This is by Maxwell's equations. J of r prime e to the I k sorry, this is r. And this is equivalent to something of this form. So now we impose that k of r. Actually, let me just restart my laptop because this is lagging a little. So we impose this condition, kr is much greater than 1, which is equivalent to saying that r over lambda is much greater than 1. So you're saying that your distance is much greater than your wavelength. So what we would then get is that, so you can make, by imposing this, you can make the approximation that this term is approximately equal to this term. So what we're saying is that n is a unit vector that is parallel to r. And if you have your system, say we take something like r prime to be this, and then r to be this, and then this would be what we're trying to get. And you're saying that this is basically r minus, assuming this is small, unit vector, the component of this along the unit vector of r. Should you have this? Yeah, maybe not. But so that lets us take the form. Actually, I might have made a mistake there. So just e to the negative ik n dot r prime dv prime. So just let me check this. So n dot r prime, that should be something here as well. and that should look like that. Or actually, there's no vector here, so it's the, you're saying that it's this minus the magnitude of this projection along this, which is basically like saying this is r prime and this is r, then you're saying that this is almost equal to this length minus this length. Right. So if we then impose that the source dimension d is much less than the wavelength, then again we can get mu naught over 4 pi e to the negative ikr, sorry, ikr over r sum of n negative ik to the n equal. So what we've basically done is expand out this term into a Taylor series. N dot r prime and dv prime. This is pretty bad notation. Let me just rewrite that into something like, I don't know, k factorial. Oh, k is used. Let's just say l factorial. It's not really important, but just hurts my eyes. So the thing is, we have that mod r prime is on the order of the source dimensions, and this tells us that, and we have the source dimensions is really small, so the dominant terms are n equals 0 and n equals 1. So we only need to look at these two terms if we want to, well, if we really want anything useful. So n equals 0, we have this term, negative I omega mu naught over 4 pi p e to the ikr over r. You get this by doing this by parts, and you use del dot j as I omega rho. And this is the electric dipole radiation. This corresponds to electric dipole radiation as well. You can sort of see it from here. Or if n is 1, this is more complicated. And as you might expect, this corresponds to the higher order sort of expansion in your field. So the first term is a electric dipole. The second term we'll see has something like a quadrupole in it. Something like a magnetic dipole, if I remember correctly. Prime, yeah. So this term is the thing we want to find. And we can actually split this into two parts. So we can split into an anti-symmetric and unsymmetric part, as we'll see really soon. So J is also the same as saying this is n dot r prime J plus n dot J r prime plus half of r prime cross J cross n. If you just use some vector identities, you can derive this. And what we can note is that this is anti-symmetric, and this is symmetric. So I don't really want to go through all the math here, but if you take an integral of this symmetric term, you can get that this term contributes something that looks like mu naught c k squared over 8 pi e to the I k r over r integral of r prime n dot r prime rho r prime dv prime. Now, magnetic field and cross A, and this is also equal to I c k cubed of now this term is actually a quadrupole, electric quadrupole term. So Q of n is, yeah, lots of algebra. And Q alpha beta, Q alpha is sum of Q alpha and beta of Q alpha beta. And this term is the components of a quadrupole moment tensor. Which you can get from here. So it's this contributes an angular distribution of one five two squared c cubed over r squared and to get this Poynting vector, we actually need the electric field, but the electric field is, you can get it by this, n cross A cross n. So that's the symmetric term. So it's just one sec. Just look at what this is telling us. The radiated power of an electric quadrupole is of this form. So that's the symmetric term. Now let's look at the antisymmetric term. First of all, let's say we have a magnetic dipole moment like term, which is, so the magnetic dipole moment is of this form. Oh dear, my laptop is lagging again. And we can get the vector potential. So this is a magnetic dipole radiation. And if you do, again, everything before, your magnetic field is of the form. Oh, this is really annoying. Just lots of results. The electric field is of the form. So if you just look at the ratio of the electric dipole to the magnetic dipole radiated powers, so this is power md. This is something of the form 2 pi a over lambda squared, which is really small. So for a much less than lambda, the magnetic dipole is much less efficient than the electric dipole, which is why your antennas would generally be electric dipole. Okay, so let's look at antennas now. So an antenna is a device that is designed to emit electromagnetic waves. So if I have a circuit that looks like this, for example. So one sec, let me just redraw this. So we have a oscillating voltage source that goes like that, and then we have coming like that. We can redraw this in this circuit diagram, and we can redraw it because the antenna part is going to be radiating out energy, right? So it's going to lose energy from the system. So we just model that as a resistor with resistance we call the radiation resistance, and this we get this by saying like it's the ratio of the radiated power divided by the square of the current running through the system, or equivalently it's this. I mean these are just like Ohm's law stuff. So I is the current at the antenna contact, and P is the total radiated power. So for example, if you take a Hertzian dipole, then previously we had that the radiated power is mu naught omega squared P dot squared over 6 pi c, and I'm just going to skip the steps and tell you that the radiation resistance is going to be 789 d over lambda squared omega. Now this is the impedance of free space, mu naught over epsilon naught. And this is true if this is valid if the dimensions are much smaller than the wavelength, which is the dipole approximation we made earlier on. And we want to look at the directionality of antennas. So we introduce the power gain, G theta phi. So this is power gain. So if we have something like the Poynting vector, then our power gain is defined as the Poynting vector in that sort of area we're looking at. So in that small region we're looking at over the integral over the solid angle. So it's like how much of the radiated power is within this theta and phi, within this arc, if you will. So this integrate over total solid angle. And just as an example, if you look at a Hertzian dipole again, the power gain is of the form 3 over 2 sine squared theta. Now, if an antenna is radiating energy, so what's going to happen is that if I have an antenna, let me just redraw that again. So it's oscillating like that. You're going to get something like EM waves coming out. But equivalently, if I have EM waves coming in, then I can induce dipoles in my antenna. I can induce potential difference. So I can use an antenna as a receiver as well. So for example, let's draw the geometry of our system. So say I have something that looks like some sort of EM wave coming in at an angle of theta. And say my antenna has dimension d, and my E field is polarized in the plane parallel to the antenna. And so say I connect my antenna to some load resistor. So we'll redraw this circuit as previously. So the total power I'll absorb from the EM wave is I squared plus R load, and it's also V squared and the power I deliver to my load is and you can rewrite this in that form, but I'm not going to. So what we'll see is actually we maximize this when we sort of match the load. So when the load resistor is the same as the radiation resistance, and you can sort of guess this would be the case, because let's say my load resistance is 0, then obviously I'm not delivering any power. If my load resistance is infinite, then there's not going to be any potential difference across it, you see. So that's, again, it won't have any power. And if I switch the position of these two, I would expect it to be maximized when our load is RR by symmetry. So now let's define an effective area of my antenna. Well, actually, if it's infinite resistance, then it becomes a voltmeter, doesn't it? Really? So you're finding the potential difference of your induced EMF. Yeah. So it's not actually zero dissipated power, but it is minimized. It has to be minimized. So effective. We define this to be the power delivered to a matched load over the energy flux density of an incoming. I'll just write it out. Flux density of polarized. Right. So basically, for a given flux density, how much of this goes as power to my matched load? And this is also equivalent to. So you can the motivation for this definition, right, is that if I multiply, so if I bring this term up here, so I'll multiply on the other side, then it's sort of like the effective energy being transferred to my system, which is the power to the matched load. You see, so that's why we call it the effective area. And when the polarization is best optimized for is best oriented for like best reception. Also, it's a bit. So for example, Hertzian dipole again. The potential difference is ED sine theta. If you look at the diagram above, and the power we deliver to the load is V squared over 24RR, and you can somehow get that it's going to be, not going to go through the math. Sorry, this is lambda squared sine squared theta over 8 pi and incident. And so your effective area looks like that. Pi. Now, what we can note is that by the dipole approximation, this is actually a lot larger than the dimensions of our dipole. And the reason you have such a large, the reason you have this is because your dipole can re-radiate. So if I have my dipole that looks like that, and I have something that's coming in, so it's going to be induced, and then so it's going to be induced, and then it's going to re-radiate out. Yeah. So this radiated field and this incoming field will sort of combine at some points, and your pointing vector would be the vector sum of both fields. And so what you can get is, at some points, your pointing vector actually points back towards your dipole. So you get a much larger effective area. Now, if you look at the results for the Hertzian dipole, you might notice that the effective area follows this relation to the power gain. Now, this is actually true for any antenna. It doesn't depend on the dimensions of the antenna or orientation, stuff like that. It's true for any antenna, and the proof is based on thermodynamics, but I'm not going to cover the proof here. But what this is telling us is that if I have a high power gain, so high directionality, then I also have a high effective area. So if it's a good emitter, it's a good receiver, and vice versa. I mean, that's sort of like what you would expect because of how radiation works. But and so now we move on to a more realistic model. So the Hertzian dipole, remember the Hertzian dipole was 2 point charges that were varying in time, and you had some current going through them, and that's not really realistic. That's not how our actual antennas look like. So for an example of a real antenna, let's imagine a parallel wire air-spaced transmission line. Yeah. So we have some voltage source, and then voltage source. We send some current down the line, and it sets up the standing wave in the line because it terminates with air, so you get the current wave going down and then reflecting back, so standing wave. So let's say our length of wire is L, and let's say we open up the last L over 2. So it looks like this, yeah. So this is L over 2, that is L over 2. And we can have something that looks like that. And this looks a lot like antenna. And this is a simple model for our antenna, our real life antenna. So the pointing vector looks like this. Ci naught squared over Now, a special case of resonant behavior is when um, the half the wavelength is L, so lambda over 2 is L, and this basically corresponds to saying that it's if you look at what your diagram. So remember, this is L over 2. So what you are going to look at is something that looks like that. You see. So it's a standing wave that looks like that. So that's resonant behavior, and in that case, you get what we call a half wave antenna. And your power gain is of the form 4 pi squared. Sorry, 4 pi cos squared. 2 pi times 1.219 sine squared theta. And your radiation resistance is 73.1 ohms, independent of any dimension, any antenna specifics. Yeah. So that's the last part for this. One last part for the antennas would be looking at an antenna array. So say I have something that looks like that. So I have a bunch of antennas that are all aligned according to along the let me just redraw this. So all aligned according to the z-axis, and you can already sort of guess that this is going to be something that looks like a diffraction grating because of how we're setting it up. But we'll see this in a moment. So that should be enough. So let's say this is z, this is x, y, and let's look at the xy plane. Yeah. So there's going to be some phase difference here. There's going to be some phase difference here. Similar geometry to the diffraction grating. So let's call this angle phi. And then so this phase difference would be Ka sine phi, where A is the spacing between the antennas. This is phi. So we're looking at the xy plane. Now, if you drive it in phase, then your electric field in this xy plane is going to have the form J equals 1 e to the negative IKA. So n, capital N is the number of antenna arrays we have. J minus 1. And this is 1 minus e to the negative I n. And, well, the reason this is important, or the reason we want to study this, is because the angles depend on, as you can see here, angles depend on lambda over A. Yeah. So if you have an extra phase difference here, so if you want to modify this phase, if you can modify this phase difference, which you can do electronically, then you can control the beam directions. And if you can control the beam directions, then you can control the directionality of your receiver. So that's an application. And the last part we'll talk about today is scattering. So scattering, an easy model is the Hertzian dipole, because if you think about atom, then you can say it's a small dipole, and you can see why we're discussing the Hertzian dipole so much. But so scattering. So if I have light coming in on a particle, then it's going to scatter outwards. That's scattering, basically. So consider a small particle with dimension A that is much smaller than the wavelength. So that's your dipole approximation already. Then if it's polarizable, then your particle radiates energy, or radiates the power of this. So this takes in, the particle takes in energy from the external field, re-radiates it. And the cross-section, or what we call a cross-section, sigma, is defined to be the radiated power over the incident flux, which is, you can compare this with the effective area we had above. And that is mu naught squared. Where E naught is the amplitude of the incident field. And usually P naught is proportional to E naught. And so, or actually, yeah, P naught is the amplitude of this dipole moment. So we get that the cross-section is independent of the electric field. So we have two cases. The first is that you have the electric field that is in the scattering plane. So we have electric field E, and B is going to be perpendicular to that, and then what you would get after that is, so your dipole moment looks like the dipole moment looks like that, P and alpha. So your result for that, the polar angle is pi over 2 minus alpha. And then the radiated flux you can get to be and the second case is when it's out of the plane. So P is out of the plane. So we have a magnetic field now. This is P. So E is out of plane. So the electric field is out of the scattering plane. Previously, the electric field was in the scattering plane. So now polar angle pi over 2, you can get re-radiated flux mu naught px squared over 16 pi squared r squared c. And what happens if we have an incoherent equal superposition, so unpolarized? Well, if we have unpolarized light coming in on a, on a particle, we'll see soon that you can actually get some partially polarized light coming out, which is something that's reminiscent of the Brewster angle in reflection and refraction. So px squared, so you're saying that unpolarized means that there's no dependence on the angle for, not the angle, but the orientation of the dipole, and this is equal to half of the magnitude. Now, let's take, or actually we don't have to take, we know that for out of plane it's going to be greater than n1. So we take n2 is n1 plus n2 minus n1. So now, if we want the total flux, right, the total outgoing flux, if we add n1, we get, so this term gives an unpolarized beam of flux 2n, because this n1 is mutually incoherent to this, and then this is the polarized flux, and the degree of polarization is so right before we end. So we first of all, we see there is no scattered flux that is parallel to the dipole moment. And this is the induced dipole moment. This is like the Brewster condition. And remember, the Brewster condition is basically if I have something like, say, water, some sort of refracting surface coming at an angle, and it going out at another angle, then this thing is polarized when this angle is at 90 degrees. And physically, what that sort of corresponds to is saying that if you look at the electric field, right, if this is at 90 degrees, then it's saying that this beam is parallel to the electric field. So you're basically saying that there is going to be some sort of longitudinal E field, EM wave, which is not possible. So you're not going to get polarization in that direction. So it's partially polarized.